This video demonstrates how to conduct the modal analysis using ANSYS Workbench. The question arises: what is a modal analysis? The answer is modal analysis is used to determine or used to study the response of the structure for dynamic loading. The next question is: what is the use? The modal analysis is used to determine the natural frequency and the mode shapes of vibration of any structure. The next question arises: what is the natural frequency? The answer is natural frequency is the frequency of the structure at which it tends to vibrate when it is disturbed. The next question arises: what is a mode shape? Mode shape is the specific pattern of vibration of a structure to a specific frequency. Let us consider an example of a rotor of a fan. This rotor rotates at 3,600 revolutions per minute. To convert its revolution in second, divide it by 60 seconds, which means 3,600 divided by 60, which will be 60 Hertz. The forcing frequency on the fan or the rotor due to the rotation will be 60 Hertz. We need to check the natural frequency of the rotor should not be equal to this frequency of 60. If both the frequencies match, which means if the forcing frequency of the rotor and the natural frequency of the rotor, if they match, then the structure of the rotor is going to resonate. This resonance will cause the increased amplitude of vibration, and this increased amplitude of vibration may lead to the failure of the structure. Let us begin with the tutorial. Create a new modal analysis file. Rename the file as Modal01. Define a new material. Let us define a new material as any plastic material, which means we need to browse for the engineering materials. Let us go for the engineering data source. Under the general materials, use a plastic material, let's say polyethylene. Pick on the plus symbol to include this material into the project. You can observe that this material polyethylene is now included into the project. Pick on the engineering data source again. Pick on return to project. Before that, let us ignore or terminate the structural steel material by deleting this material. Pick on return to project. Right-click on the geometry and import a CAD geometry. Right-click, pick on import. There is already a file called as rotor-01.step is there in the temporary memory. Let us import this file. You can observe a tick mark in the geometry, which means the geometry is loaded. Ensure the unit system. Pick on units. Make sure that the unit system is millimeter, ton, seconds, degree centigrade. Right-click on the geometry, pick on Edit Geometry. The geometry will be now opened in a design modeler. Ensure the unit of the ANSYS Workbench as millimeter. Pick on OK. Once the geometry is loaded, pick on Surface Bodies equal to No. Solid Bodies equal to Yes. Line Bodies No. Pick on Generate. This will import a CAD geometry into the ANSYS Design Modeler. Let us extract the mid-plane or the mid-surface for this rotor structure. Pick on Tools. Pick on Mid-surface. Select a face pair, which means select the top face of a blade, press hold Ctrl, select the bottom face of the rotor. Now we have selected one face pair. Pick on Apply. Under the selection method, pick on Automatic. Now, under Find Face Pair Now, pick on Yes, Add Face Pair. Automatically, 3 face pairs got selected, including the face pair selection which we did manually. The rotor center hub is not included for the mid-surface extraction. Hence, pick on the face pair here and pick on the surfaces. Pick on Apply. Similarly, pick on the surfaces. Pick on Apply. Ensure that the control button is press hold while selecting the multiple surfaces. At this stage, we have 7 face pairs. Pick on Generate. Observe here carefully. The mid-surface of the fan is now extracted. We are going to export this mid-surface for the modal analysis. Return to the project page. Pick on the model, right-click, pick on Edit. The mechanical window is now opening. The attach status can be found. It can be seen that the geometry is now imported. One key observation to note here is the geometry or the rotor is not assigned with the material. That's the reason why you can observe the question mark symbol before the name of each body. Select all the bodies by pressing hold Shift. Under the material assignment, pick on polyethylene. Now you can observe a right mark or a tick mark which says the bodies are assigned with the material. To proceed further, let us define the mesh. Right-click on the mesh, insert, pick on sizing. Let us give the size of the element for all the geometry as 5 mm. Then pick on or right-click on the mesh, pick on Generate Mesh. It can be observed that the whole rotor is meshed. The mid-surface is exactly at the center of the thickness of the mesh. Because we have extracted the mid-surface, we have not assigned the thickness for the mid-surface because it was being recognized by ANSYS Workbench automatically. Now, let us give the boundary conditions for this rotor. Right-click on the model, pick on Insert, pick on the fixed support. We are going to fix the center of this rotor. Hence, use the edge selection from the geometry selection filter and pick on these edges. Pick on Apply to confirm the geometry selection. Observe the fixed support is at the center, which means we are analyzing this rotor at the static condition, which means now the fan is not rotating. That's the reason why at the end of the rotor shaft, we are going to fix the rotor. Having understood about the meshing and the boundary condition, let us pick on the analysis settings. Under the maximum number of modes to find, enter 10. Under the solver type, pick on the direct solver. Once the necessary analysis settings are done, it is a time to solve the problem. Right-click on the solution, pick on Insert, pick on you can pick on solve directly. The ANSYS Workbench solution status is in progress. It can be observed 10 natural frequencies which are computed by ANSYS. Let us see what is the mode of this particular natural frequency. Pick on the first natural frequency, right click and pick on create the mode shape result. You can observe in the outline tree total deformation is included. Right click on the total deformation, pick on evaluate all the results. To animate this behavior, pick on the animate button, which means the rotor is going to vibrate or respond in this manner at its first natural frequency, which means any disturbance around the rotor, if it is 86 Hertz, then the rotor will behave in this manner. Or if the disturbance around the rotor is say 167 Hertz, then let us include this result. Before that, we need to stop this animation. Come back to the tabular data, right click on this, pick on create mode shape results. You can observe one more total deformation is included for the mode shape of 5. Right click, pick on evaluate all result. It can be seen the different behavior now. Pick on the graph, pick on animate. You can observe the rotor is going to behave in this manner when it is being disturbed with a frequency of 167 Hertz. Similarly, it has infinite number of natural frequencies. Any of the forcing frequency which equals the natural frequency of the system, then the system or the structure is going to resonate. We have calculated that the rotation of this rotor is 3600 RPM. When we divide it by 60 seconds, we got 60 rotations per second, which means the forcing frequency is 60 Hertz. Under the tabular data, we have seen there is no frequency which is near to 60 Hertz. Hence, we can say that the rotor of this fan is not going to resonate and there will not be any potential failure observed in the rotor structure. The modal analysis can be conducted for a single bodies or multiple bodies also. Thank you for watching this video. For more videos, please subscribe my channel. If you like this video, click on the like button just below this video. If you have any queries, please feel free to contact me at this mail ID. Thank you.